Dr. Chongwen Huang, thank you very much for accepting our invitation. Again, we are very delighted to have you here and to deliver this seminar. And now the floor is yours.
Thank you, Daniel. Introductions. Thank you your invitations. So good afternoon, everyone. So it's so great to have talking here. So this is work was done by collaborated with the SUTD and THz researchers. So my name is Chongwen Huang, come from the Zhejiang universities. Because I love the physics and the math very much. I think the physics and the math is a most important driving force for any information technologies. So I'm also very interested in the emerging technology like the computing and the sensing then. So I'm giving the name of my lab as physics and math empowered intelligent communication, computing and the sensing lab. So that's a brief introduction about my research lab. So okay, let's go back to today's talking. So my talk is titled Holographic MIMO Surface for the 6G wireless communications. And in this talks, I will introduce the past, present, and the future of the emerging technology named the Holographic MIMO Surface. And but I also will be explaining the fundamentals of this new technologies, how we're building the basically channel modeling and deliver some recent research results of my research lab. So today's presentation has 4 parts. The first one, I will introduce the past of the holograms. So then I will present the present of the holographic MIMO. And then I will give an example how we have the channel modeling for the HMIMOS communications. But the last part, I will introduce some recent results, research results. So let's go back. What's holograms? This work was first proposed by the Dennis Gerber. He applied the patents or authorizations in the British in the 1947. The 2 years later, he had publications and gave it a name as holograms. In these works, he first gave the definitions of the hologram. So the name holograms is not the unjustified as the photogram contains the total information required for the reconstructions of the object, which can be the 2-dimensional and or 3-dimensional. So in this sentence, we can say the holographic contains the total information. So what's the total information? So total information for any signals, we use the amplifier and phase to describe the total information. But for the light signals, the amplifier is easily to record. But the phase, how we to record and recover the phase, it is not easy because the phase of the light, it means the wavefronts information of the whether it is high or low. Like see these fingers. So from these fingers we can record the high or low of the front information. Just dynamics fingers. So go to the math basically. So we use the OXY to denote the light field. So and the O1 or O0 to denote the amplifier atoms of the light field. But the phase is very similar. it is very common. So use the is this term to denote. But if we get the modular of these signals, the phase atoms will be disappeared. So why? Because the modular just to get the amplifier. So how we to record and recover the phase. So this is so we introduce it needs to introduce the reference light and use the reference light to interfere with the object, the light, so that we can to store the phase information in the strip. So like these fingers to show the principle. So in the math to describe this in the math to describe the whole process. So we can to use the I xy to denote the original light site and the R as a reference light. So we just to get the IXY is equal like this, and then to get the square of the light signals. So we can after the append, so we can get the phase terms. This is the basically principle of the holograms project. So after I introduced this principle of the project, so then we also can to use the meta surface to implement the hologram. So this relevant the results can be see the list to reference here. So it is common for the to hologram images and the projection. So the next part I will introduce the present of the holograms. So here I just to give abstract the holograms. I just to divide the two catalogs. One catalog is focused on the applications. Another is focused on the technology. So as we all know that the holograms, it means that the immersive AR, VR, and the any holographic projector also including the 3D VR, AR programs, games. So in another way, in another aspect, from the technical perspective, the holograms, it means that the holograms images. I also to investigate a lot of the iterations. We give a summarize for the how we to implement the holographic projections. The one way is the traditional optical holograms. Another is the digital holograms. The third one maybe is use the computational holograms. So the holograms is very promising for the 6G. So recently, many of the white papers giving a lot of the application scenarios of the 6G holographic MIMO communications. So like this in the Chinese mobiles white papers, and he giving a development trends of the 6G holograms communications business. So it contains many aspects. The first one is the multi-dimensional interactions. Another one immersive holograms. Then is the ultra intelligent information networks, and then it can have the high quality interactives. and so on. Maybe I think it's very promising for the 6G. So next, in another many people also proposed another technologies maps. So it calls the intelligent holograph radios. It implemented by the photonics. So it like this. So in this technicals, I also think it's a promising technology. But it also this technology also was written in the white paper on the 6G or visions and potential technologies of the China's the promotion groups white papers. Before these papers, before these white papers, I know the holograms from these white papers. These white papers were published by the Petwave Cormier. So it was released in the 1990s. This in these white papers, it giving definitions of the holographic beamformings, and I think it's very similar with the RACE, is a Reconfigurable Intelligent Surface. It giving the definitions of the holographic beamformings is a new dynamic beamforming techniques using the software defined antenna. This is very similar with the RACE, I think. But another different with traditional technology, it also giving the abstract about the architectures of the holographic memos and the phase array and memo. So from these tables, we can see the holographic beamformer is very different with the memo. So in the holographic beamforming, we just have the one RF and one transmitter and receiver. So we have a lot of the tuned element to control the phase. I think it's very similar with the RACE. So more popular definitions of the holographic memo communication was proposed by the Andrew Pizzo and the Thomas Mazat. So he has a lot of papers to giving a definition of the holographic memo communications. I just give it here. So in these papers, he told us just to imagine a array with a possibly uncountable infinity number of antennas in a compact space. We reference these systems as a holographic memo. I think this is just a very easily to describe of the holographic memo antennas, but not very comprehensive definitions. But here for me, I also introduce one technology called the holographic MIMO Surface. So based on this concept is defined based on the race. We just to define the actual race as HMIMOS. So very similar with the holographic project. We just to have the two steps. One is a recording, and another is reconstructions. The process. So then here I think the previously main concept of the holographic MIMO surface is not very good. So here I just giving a new comprehensive definitions. We think the holographic wireless communication is a physical process of the realistical and the completed recurring the 3D target things that will be transmitted and receiving, and with the help of the new holographic antenna technology. I think the holographic alternate technology, it means piezo's holographic MIMO. So the wireless and the wireless electromagnetic signal technologies, which is at the same time can be realized 3D dimensional remote dimensional dynamic interactive of the people's objectives and their surrounding environment. So maybe someone will be asked what's the difference between the HMIMOS communication and the Memo communications. Here I just to giving some comparisons. So firstly we compare the coherence. So in the HMIMOS it should be the ultra high, but for the Memo it will be lower. But for the in terms of the multiplexing resolutions, so I think the HMIMOS is very high because it is usually implemented by the optical and the phonetics, but the Memo is very lower. But for the aperture, it is well known. It is continual aperture and nearly infinity. But for the Memo, it is decreased aperture and limited and this discontinuous. But for the computing models in the HMIMOS, we cannot use the relay models, but we need to use the free cell models. But because it is in the near field, but for the Memos, it will be the far field. So this is a table to show the many difference between the two communication systems. Here I just giving some method for the future research direction for the HMIMOS. So the first one, I think, is the channel model. See, so it's a hard one because in traditional communication we have the far field communication models, but in the future's HMIMOS communication, it will be the near field communications or mixed field communications. So we need some new models. So another one is the coupling. So the coupling is another big problems for the HMIMOS because when the element will be space element of the HMIMOS will be decreased and the coupling will be increased. So then another physical technology is a holographic beamforming design because we have the near field. So the holographic beamforming design in the near field is very different with the far field. So I think we also need to consider the multi-user interference and information transmission or transmission between the continuous surface. How we to get the continuous design the information transmissions and receiver continual surface informations and another problem is access because we have the continuous surface. How to access the continuous surface? Maybe I think we need the new technology. So then go to the next part. So in this part, I will to give an example how we to get the channel modeling for the HMIMOS communications. So this part comes from my co-authored paper. So it's listed here. So if you're interested, you can go to the archives and the Elsevier website. So here we consider this system. So in the transmitter, we use the continual surface. Continual surface is also called the HMIMOS. So we have the big MMOs, HMIMOS, and in the receiver we have the smaller HMIMOS. So then if we use a plane wave is depending on the HMIMOS from the assume angle and the activator angle, and we can get the transmitter vector becomes this these equations. So it's very similar with the minimal wave, but the key theta is in the three-dimensional or transmission surface, but this is the difference with millimeter waves. But similar, we can get the receiver vector is written like here. So then we can get the model. The channel has three parts. So the first part is the source response, and another part is the receiver response, and the last part is the angular response. And the angular response, because as we have mentioned, the AS, the source response and the receiver response is very similar with the millimeter wave, but the angular response is different. But how we calculate the HA for these channels, because we have considered the continuous surface, we need we could not get the channel matrix. We just have the integral of the transmission and the receiver. So with the integrations region D, it can be written like here. So then we can get the HA. HA also has a three parts. The first part is S. S is a spectral density. Density can be calculated like this, and another one is a spectrum factor A. A is arbitrary real valued functions, but W is complex signals like the Gaussian signals. So like this. So use these functions to denote the HA. But how we calculate is the key steps is to calculate the S and the A, right? So then we get the for the individual users, we can get the transmitter vector and receiver can be right here. So the RS and RR is the receiving and the sending space. So then we can get the HM. We just because we just to remove the integral, because the integral is very hard to calculate. But how we to remove the integral? We just to adopting the Fourier planar wave scenery applications. We have this one. So we just to get approximate like this. So the Fourier coefficient is can be read here. So with a variance given here, but the variance is also has a integral. How we calculate this is more important for the channel modeling. So because the detail is very complex, we just provide offered in our papers. So here I just skipped this calculator steps. So that if you're interested, you can go to my my papers. So then I just giving key steps here. So the variance delta square. So just giving here. So we also to calculate the integrations regions of the receiver surface like here. We just to get the integral and to get the approximate somethings and to calculate the delta x. Once we have the delta x, we can calculate whole channels, and then we can get the channel models of the HMIMOS. So here we also to simulate our considered systems. So in these figures we compared the eigenvalues and the eigenvalues number. So because we considered the mutual coupling. So from these figures we can see with the increase of the eigenvalues number, but with the increase of the antenna space, the key is denotes the antenna space. With the increase of the antenna space, we can see the eigenvalues numbers will be decreased. So that it means that we have the smaller receiver antenna space. We will have the greater of the channel cooperated, and the smaller number of the independent channels. That's why, because the mutual coupling will be damaged the performance. So in these fingers we have the similar results. Different with the previously fingers, we just we have the pre-codings. We use the two pre-codings schemes. The first one is the MMSE, another one is the zero forcings. We also compared the spectral efficiency with the SNR. So we also to compare the different the antenna space. So the red line denotes the MMSE's performance. So we can see here. So increase of the antenna space from the lambda divided 6 to the lambda divided 12. So we can see the performance will be decreased. The performance will be decreased from here. So we can see it means that we reduce the space of the transmitter antennas will be reduce the spectral efficiency. This is we consider the linear mutual couplings. The mutual couplings has impair the spectral efficiency. That's the main conclusion we would like to show here in these figures. So we can see another work. This work was done by the Mazat, but this is totally different the results. From these fingers, we just consider the mutual couplings, but we can but in the first fingers in these fingers we can see the antenna space will be increased, but the power transfer efficiency will be decreased. It means that this is a totally different results with our papers. Why? Because here he just considers the coupling, but the coupling here just will be improve the power transfer efficiency and the directivities. But why? Because here he just to think the coupling can be used, can be leveraged. So, but in our papers we just treat the coupling as an interference. So will be so that's the main difference. But if we leverage the coupling, we can get the very promising results. So in this this is the main conclusions. This work will be shown in his work. So the last part I will be giving some results about my research groups about the electromagnetics field information theory and near field communication. But my group has already published one works, and we have submitted the three works. And the first one we can see here. We also consider the coupling, but the coupling here we can see in these works we have the similar result with the two tops. So we can see here we just to consider the different scenarios. So we simulated the diversity with vs the antenna numbers. So we consider the two cases. The first case is without the coupling. Another case is with the coupling. So from these figures we can see here. So the without the couplings is here. but with the coupling is here. But we can see in these fingers, but the coupling will be also decreased the diversity. But in these fingers, we can see with the coupling, we have the we assume we have the 100th efficiency, but we get the high capacity than the without the coupling. That's why the two fingers has two different different results. But why? Because in here we don't leverage the transmitter efficiency, but in these fingers we leverage the power efficiencies. Here we treat the coupling as a good factor for the capacities. We can see the coupling also can increase the capacity. But in the next results, in the next steps, we will be research how the couplings how we can to leverage the couplings. So we will be to propose some things to take full use of the coupling. How we to leverage the coupling to improve the capacities in the next step. So another work is about the near field communications. As we all know, here is a definition of the near field and the far field is defined by the relay distance is denoted here. So D is denotes the array aperture and lambda is the wavelength. So if we use the rays to as a transmitter of the receiver, so we can get the high aperture gains. It means that D will be larger and larger. And but also we can use mmWave and terahertz. It means that the wavelength will be decreased. In a word, so in the futures communications, we use high frequencies communication and the rays and all holographic memos. It will be make the original or far communications to become the near communication. That's why the near communication is so important. So here in these works, we also derived some results. In the we give it a theorem 1 to show the near field degree of the freedom. In these figures, we can in this equation we can say we just to look at the more degree of freedoms in the near field communications. So here in these papers we also to plot the degree of freedom compare the traditional one. So in these figures we can see the the internal circles we is the memo freedoms degree of freedom. In the outside of the circles we show you the near field degree of freedoms. We can see in the near field communications we have the 13% degree of freedoms improvement. But in these figures, we also to plot the gain. In this figure, we also get the similar results. We also can get the 13% gains improvement. So in another work, we also gave a new definition of the effective degree of freedoms. In these definitions, we just use the eigenvalues of channel to approximate the degree of freedoms. So in this work, we just to show the EM degree of freedoms we as the distance. So from these figures we can say with the increase of the decrease, but the freedoms will be decreased faster. So then another figures to show that the one has the different distance, but with the increase of the antenna or the antenna of the source of the receiver's antenna. So when the distance was fixed, but we increase of the antenna, but we will be the degree of freedom will be reach the floor. But why? Because the distance is determined is the main factor of the degree of freedoms. So in these figures we have the similar results with our previously work. So that's two papers to show why we do the near field communications. That's from the figures we can see in the near field communication we get the more spectral efficiency and more degree of freedoms. So here I just giving conclusions of today's presentations. So in these presentations, I just go back giving some the histories of the holograms and giving a new concept of the holograms, and we also giving an example how we build the EM channel modeling in the multi-users HMIMOS communication systems. But when we consider the mutual coupling, we also verify the closer space antenna space will be impaired the performance of the SE. But we just the conditions here is we just to treat the coupling as interference. If we remove these conditions, the mutual coupling maybe can to improve the diversity or capacities. So related work also verifies the mutual coupling can to improve the power transfer efficiency and the directivity. But in the following, how we to design the mutual coupling, how we to take full use of the mutual coupling to improve the capacity is a key problems in the following. But one key conclusions in here. So the holographic MIMO can make the near field communication as a potential meaningful scenarios in the futures, and I believe it maybe has a gain more than the 13% of the degree of freedoms and also capacities. So that's all. This is the main results I would like to present here. So thank you for your listening here. So if you have some questions, so you can hands up. So
thank you very much, Chongwen, for your presentation. So now we'll move for the QA section. So if there is any question, please feel free to write the question in the chat box. Okay. Okay, I have some questions. Actually, this is a very interesting and emerging research topic, right? And I mean, in parallel with holographic MIMO, actually, people use reconfigurable intelligent surface and holographic MIMO surface interchangeably, right? But what is the difference between reconfigurable intelligent surface and holographic MIMO surface? Is there any difference, or people can use interchangeably with no problem?
Okay, thank you for your questions. So in my way, I think the reconfigurable intelligent surface is a active reconfigurable intelligent surface is very similar HMIMOS but the passive race is very different the HMIMOS, as you know here. But for the active race, so active race maybe, but I think the difference is
yeah, people use for active race use another term, if I'm not wrong, is large intelligent surface for active race, right?
Yes, yes, but holographic MIMO surface, I think is more general, maybe because the holographic MIMO, some people think is implemented by the photonics, but the race is not. But I think the holographic MIMO is more general. But the race is means the meta surface is implemented by the meta surface, right? But HMIMOS maybe I think it can be implemented by the more ways, like the photonics, like the race, like the metamaterials and others. But from the here, we also from I think the channel model is also another difference. So the channel model, the race is also use the relay and lace relay, and but the HMIMOS we cannot use here. So we just maybe we need to use the free cell and consider the LED features and some things, I think.
Yes. Okay, regarding the channel modeling that you talk about, actually in your slides when you presented, I mean the how to modeling, from what I understood, you use some approximations of plane waves, right? Series expansion. And my question is, does it work for both near field and far field assumptions? The channel modeling that you provided, you show us.
I think it can work both as the near field and far field, because the near field is different, but the HMIMOS can still work in the far field, but the traditional Memo cannot work in the near field, because near field the Shannon capacity, I don't think the Shannon capacity cannot use the near field, because the Shannon capacity is describes the far field. But maybe we need to modify the Shannon capacity in the near field. In this way, I also think the HMIMOS maybe is also is a potential solution to beyond the Shannon capacities. I think it's a potential way, but I'm not sure. But I think is potential. But so I think for the calculator, we also can use the Shannon capacity to calculate the HMIMOS and the Memos. But maybe I think it's not accurate, because you just to plot the finger is okay, but maybe the real capacity is not very tight or very close with the Shannon capacity. But I think it can use, but not the accurate.
Yeah. But can we use the wave propagation formulated in terms of plane waves, regardless the distance between the transmitter and receiver?
Yes.
Because with yes, then I mean it applies for both for far field and near field, right?
Yes.
Okay. Okay, let's see if you have any questions. No question. Okay, another question that actually this for you provide some of your folks on how to integrate holographic MIMO with THz. Since This is another, emerging technology, and how we can make it in harmonious integration, holographic MIMO with terahertz.
Sorry.
Yeah, my question is how to integrate harmoniously a holographic MIMO with terahertz.
Can you rephrase a question? So I'm sorry to cannot catch your means. Also, sorry.
Yeah, terahertz band.
Okay.
Okay. So how to integrate holographic MIMO and communications? What are the challenges, and how you can make it feasible in practice, holographic MIMO with terahertz?
Okay. So I think the risk is one way, but I think but I think the magnetic series is a basic series. I think we need to combine the electromagnetics and the communications, and to put them together, and we also to pay close to the circuit design. We put the three aspects together. I think we can to make the holographic memos to go ahead. So
okay.
Sorry.
Is there any is there any,
sorry,
available?
So I cannot hear you clearly.
Okay, let me repeat.
Interrupting.
Yes. So let me repeat. My question is there an available hardware fabrication methodology for holographic MIMO? Did you hear me?
Yes. For the fabrications methodologies, because I'm not sure, because I think the I don't have the many research on this aspects. Maybe I think it's more focused on the materials. So I think it depends on the metal materials development. Yes. Another way is use the arrays to replace a new idea is to use the print, the metal print, a continuous metal print to control the metal print. But now, but in the real case, we cannot control the metal print. But in the future, maybe we can use we can control the metal print. Metal print can be seen as a holographic MIMO surface. So I think it's a good way, but it depends on the materials and the fabrication technologies. I'm not sure, but I think we can get the technology to implement to the HMIMOS. So.
Okay, we have one question from the participants. The question is: the main reason for applying a configurable intelligent surface is that the direct link between the transmitter and the receiver may be blocked, and RRS can create the additional link. Is a holographic MIMO also suitable where the transmitter and the receiver is blocked?
Yeah. Yes.
Yeah. So actually, I think the principle, even though there are some difference, I think the functionality and the principles are and have the same goal and are almost the same, right?
Yes, but if we use HMIMOS is also suitable for the transmitter or the receiver is blocked. But I think it's a little different with the race, because we can race as a passive reflector, right? Passive reflector, but the HMIMOS is just to as a transmitter or receiver. But maybe we need to integrate the HMIMOS and the race to a new systems. We can also build the connections. So I think this is a good way. But just only use the HMIMOS, I think it cannot to remove the blocking.
Yes.
Because HMIMOS, I think is a placement for the memo, for the message memo, but this is also different with the race, because the race is as a reflector, but the HMIMOS just focus on the transmitter or receiver. It is an active one, so maybe I think it can use it for the blocking to remove the blocking. Maybe it's not a good way. So I think the race is it's a good way to remove the blocking.
Okay. Any questions? Okay. Another, I mean, actually, a general comment that you mentioned in your presentation is about the channel estimation, right? And the channel estimation is indeed a very, I mean, it's very challenging, and because we have a very large, I mean, channel in terms of dimension. And could you please elaborate, I mean, the main techniques and using compressive sensing, deep learning, and about the training data? I think it's very important because I suppose you require a large amount of training data for estimating the channels. So could you please elaborate and provide your thoughts on this challenging?
So that's a good question. So yes, as you mentioned, the channel estimation is a keen technology for the any physical communications, but it is also very important for the HMIMOS, because the HMIMOS we have the infinities alternatives in the receiver or in the transmitter. But another way, so we need to a new method. I think the new method is called the channel estimation free. So we don't need to the channel estimations. So because we do the channel estimations, the payoff, so the workload is very high. So we cannot because the channel is continuous. We cannot get the accurate channel estimations. Why not we get the channel estimations? Because the channel estimations information mainly for the beamforming, right? Because if we know channel estimations, we also can do the beamformings. That's fine. So there are a lot of the methods to do the channel to do the beamformings. So for the beamformings, so we just like the word filling, power allocations, just as example. So we just need the SNR, right? If we have get the users SNR, so we get the SNR, get the NR. If once we get the SNR, so SNR is a high, is a lower. We just to get the lower. If we get the lower SNR, so it means the channel is not good. So we're giving the less power. But if we got the SNR is high, maybe we use we allocated more powers. That's a new, I think is a new method to do the beamforming. So we just to do the beam scan. So the beam scan is easy to do because we just to get the standard signals. The users to send the standard signals to the base stations. So base station gets the standard signals to calculate the SNR. So SNR, once we get the SNR, we can do the beamformings. Like the that's one problems. That's one method. Another method is called the random beamformings. So we don't need to get the channel animations. So maybe we can use the random beamformings. Random beamformings another way to get the beamformings method. So that's two ideas I would like to share. So here, so for the channel animations method, I think is not good. It's very hard to get for the HMIMOS. But for the race, maybe we have a lot of methods. Yes. So we use the compressing things and the tensor decomposition otherwise. But for the HMIMOS, I think it's more difficult. So maybe we need to the new solutions like the channel machine free solutions and something else. So that's my ideas.
Yes. Okay. Let me see if you have questions. No questions. Okay, so let me. Okay, I have another question. Actually, again, is a general comment that I would like you elaborate about it. Is I think another challenge, and I'm not sure if you mentioned in the presentation, is refers to the deployment of holographic MIMO surface, okay, in the propagation environment. In I mean, similar to IRS, we have distributed, configuration and centralized configuration, right? And
yes,
for the centralized configuration, usually it requires a massive amount of information, control overhead information to be to communicate to the to the controller, central controller. So I think for holographic MIMO, it's more convenient and suitable to consider the distributed configuration, right?
Yes. Yes.
Yeah, but this is you also pose some challenges regarding the algorithm design. For example, if you have a more holographic MIMO surface being deployed in the network, this will increase the algorithm design. So could you elaborate and provide your thoughts on this deployment part?
Okay. So thank you for your questions. So because as you know, the holographic memos were just to deploy it in the transmitter or receiver, but for the distributed but if we distributed the HMIMOs in the networks, I think is a good way. But the control and configures is more hard to control because it is a continuous surface. So it means that is every point we need to control. We need to change, right? So I think we need to divide the different groups. So maybe we just to use the continual methods to control the parameters, and to maybe also we can use the continual phase we just to adjust to change the phase by the continual ways. So this is one way. So another way I think we can to change the so I don't know how to say, so sorry. So because to see these fingers, so we can see from these fingers we just has the one RF genes. So in the different in the distributed networks, we just to use the cable to connect the everyone. So and the one cables just to use a continuous in a continuous in a range. So we can do send the control command to each distributed HMIMOS, and then we can I think we need to the new technology to control
yes.
the network. So maybe it's sorry it's hard.
Yes, it's fine. Thank you.
Okay.
Okay, any questions from the participants? No. Okay, so I'm going to move for the end of this telecom seminar. Once again, I would like to thank all attendees for joining us in one more telecom seminar. As I mentioned in the beginning of this seminar, we are organizing in a bi-weekly basis these activities, and we are always invited active researchers, renowned researchers to discuss some of these emerging concepts, okay, related to wireless communications. And for today, we had the great pleasure to have Professor Chongwen Huang from China, who discussed about holographic MIMO communications. So thank you very much once again, Chongwen, for your presentation. And so this presentation has been recorded and will be available in a TII YouTube channel very soon. Okay, so for those who want to watch again or to inform the other colleagues who are not able to attend this seminar, so feel free to disseminate these activities which are being organized by the TII. So thank you once again, everybody. Thank you, Chongwen, for your presentation, and see you in 2 weeks, right, in our next telecom seminar.
Okay, thank you, Daniel. Thank you
for
your
very much. Thank you.
Thank you
Bye
for
bye.
your listening. Thank you
Bye.
for your invitations.
Bye.